Hello, how are you?
Oh, only me.
You are the first.
Yeah.
D, welcome back. Hi, Professor. Jacques. So, welcome to week 13, lecture B. Okay, so we have Kevin. Maybe he's in the middle of something and we can start. So, welcome again, and week 13, we are in the end part of this semester. So today we are going to review what we learned last time. After that, we are going to run through examples regarding a reduced order observer control. So a few things in order. First of all, FISP, and we have all decided the topics. So we're going to have letter grades. We are not going to have a final exam. And so please spend enough time on FISP. And try to be an expert on the topic you choose and present something nice, okay? And here are the topics. D is going to talk about monotonic tracking control for multivariable systems. That could be useful for his vehicle project. Kevin will be a linear periodic system as well as periodic controls. I'm going to talk about bracket order linear system where we have a MIMO toolbox you can use. Carlos is going to talk about digital twin for a MIMO platform. It's called FELP. Very interesting platform. Yak is going to talk about optimal disturbance reduction in linear multivariable systems. Finally, Howie is going to talk about positive linear multivariable systems. So I'm going to put the first group 3 in one day and the next 3 in the second day. So we are going to use the whole week, the last week, to do this. So last time we went through some definitions, concepts regarding state feedback control. We learned that state feedback control will never affect the controllability, but it could affect the observability. And we talked about pole placement, observers, structure of the observers, and the design is actually due to that of the state feedback. So you have 2 things to decide for full state feedback. Full state feedback. So U is minus KX, full state feedback. How do you decide the K? That depends on what do you want, where you put your poles. So then there's a MATLAB command called place, okay? Place to do the job. On the other hand, so if only Y is available, how you can reconstruct X hat. So this is called full state. I use the word full means I use all states, okay? Full state observer, okay, observer. So combine observer and state feedback so that we can have a closed loop design, okay? So this is a fundamental skill. It's a very basic skill that you need, okay, for the MIMO state space design. And the separation property means the structure is something like this. It's a block diagonal like this. So this is a state feedback, is observer dynamics. So there's something here, okay? So this is the structure that leads to the what they call separation property. You can design them separately. So here are the architecture. Remember, this whole thing has input is U, input is Y and U, and output is the state estimate. So open loop system, then this is a closed loop system. So I said this is a static controller, and this is already a dynamic controller. So which means it's a C of S, okay? CFS. This is dynamic, it's a transfer function matrix. So this is also a transfer function matrix, okay? All right. There are so many design flexibility in here. So this design of MIMO controller is never a trigger task. However, from this control architecture, we have a systematic way to design CFS, systematic way. So that's why state space is popular in the MIMO sense. For input-output model of transfer function matrix, the design is never straightforward, okay? So control is a state feedback of the estimated states, okay, this one. So then we zoom in, we are going to see this is a block diagram, in the block diagram of the observer design. Again, going to this block diagram is U and Y. So here's the U, okay. Inside is, you can see something very close, that you have a SI minus A inverse, you have SI minus A inverse. I want to say this is called a copy of the dynamics, okay? Copy of the dynamics. So open loop system, again, this is just more detailed version of the previous block diagram called architecture. But in this green shaded area is dedicated estimator, okay? Again, what should I add? Full state feedback, full state estimator. So all in equations, we write state dynamics and estimator dynamics, and this. So, but this can be combined if you use X in augmented state, like this is written in terms of x hat, okay, x hat, and now you have a upper triangular, lower triangular block partition matrix. Closed loop system. What is when you talk about closed system, you need to, what is the in, what is out, okay, out. So this is the aerodynamics. This is called aerodynamics, okay. So we want to do a closed loop dynamics, that is so it's a Y over U, Y of reference, okay. So this, you can see the block partition apart, and this is 0, okay. So this is system dynamics, meaning you don't have the U anymore, you remove the U. So this is autonomous system. No U. No U. Then if we do transfer function, then we need to identify what is input, what is output. So I would like to say the compensator part, output is U. What is input? Input is Y. Output is U. Input is what? So this is output. Okay, this is my output of a compensator. This is my output. So what is the input? It's here. Okay. Here. Okay. Yeah. So in this case, we're going to get something called a GC. It's what I call CIJ of S. Dynamic controller is written in this form. Okay. So basically, we identify this is input, this is output. Okay. Then this one is actually written as Y of S divided by U of S. But in the MIMO case, you write this way, it's actually wrong. I don't like it. Okay, you should not write this way. You'd always write Y of S is G of S, GC of S, and U of S. So this is a MIMO matrix. This is a vector. This is a vector. Vector. This is a matrix. So how come you can write a vector divided by vector? So makes sense. So that's a closed loop system for, that's the compensator transfer function. What is a closed loop system with the original states? So here we have a closed loop state equation. You don't have a U here anymore, no U. And here you have estimator dynamics. So adding together, you can write. So this is becoming without no controller, no control signal. Everything is lumped. So this is a familiar form. Okay. So this is what they call closed loop systems with the augmented states. Okay, augmented states. But augmented states here actually is a CX. Okay. So with this, you will be able to do transfer function. So design observer feedback system is the overall system has eigenvalues of union of this one and ARC. Pick up eigenvalues of this one, do pole placement, like a pole placement. And okay, you can do something similar, like a pole placement observer gain. Separation of the solution into separate design for both state feedback and observable, so they can design separately. So today, we're going to run through a full order observer design example. Then we are going to talk about reduced order, okay, observer. And also we are going to do a reduced order observer design. So let's go through a full order observer design. And so we have A, B, C. So that's a block diagram. So writing in original system is this one. But remember, if you write this one, you should write something like this. So this is my X hat, okay? This is my X hat dot, okay? X hat dot. So this is my observer, okay? Dynamics. Then by writing a combine here, so this is observer dynamics. And so you have if you remember this one, so you have a U Y as input, U as input, X hat is output. Okay, X hat is output. So that's an observer, okay? And this is a full state. But what we didn't plot is original system. So original system, you should get familiar with this one. So you have 1 over s is integration, and when you have x dot in here, you have x, okay? So then you have x dot equals ax, so a is here. You have ax, and you have u in here. You've got a b in, so ax plus bu, you have x. So you put a c in here, you get a y, okay? So that's a block diagram. You hook up this y and the u and the y and the u here, y and the u here, u and the y here. So you got the all closed loop system. So let's do an example. This example, actually, if you write, is something like you have x equals, the x1 equals x, x2 is x dot, x1 dot, okay, and 1 dot. So here is like y is equals x1, okay, x1, 2 times x1, okay, 2 times x1. So no, this is x is already used. I'm sorry, I wish to not use this. So let's say this is this is a z, okay. This is z dot, okay. Yeah. So if I write, this is a second order system. So basically we can write x2 dot is z double dot will be minus 2z minus 3 z dot plus u. So remember, this is nothing but z double dot plus 3z dot plus 2z is u, right? So I give you an example like spring damper system. So the displacement here is z, okay? So this is my u, okay? So we write, this is a simple MSD, mass spring damper system, okay? Spring damper system. Or you can see this is nothing but some sort of cruise control, okay? If you have a car, you know what is that, cruise control system. So my y is 2z. That's a position feedback. I don't have a velocity feedback. So we design a full order state observer with observers pole at -10, -10. So what we should do? We should do h is h1, h2. So lambda I minus AHC. So this is a C, okay? Is giving my characteristic polynomial like this, okay? However, the desired characteristic polynomial will be s plus 10 squared because it's put in the same place. It's fine. We have 20 in here, 100 in here. So this should be 20. This should be 100. Okay. By solving that, you know the h is this. So then observer equation put all together. We copy. So we copy the system dynamics. This is my. So I have y is available, u is available. So y in the front has a h, and b is known as 1, 0, 1, and a minus hc will give you this. So then, given any initial x hat 0, then I can guarantee that x hat infinity will be x infinity. So will converge, right? Asymptotically, because the eigenvalues of this guy is -10, -10. Okay, so that's my observation, observer's equation. But original system, this is my original system. Okay, it's MSD, open loop, a mass spin damper system. And now I can estimate my x1, x2. But remember, in this case, y is 2, 0, x1, x2. That means y equals x2, x1. Also means x1 is half of y. You can already get it. So that's why we don't have to estimate x1. x1 is already available from y. But here we ignore this fact. We just assume we don't. So we just estimate it. So we just do it. Okay, so I got x1 hat, x2 hat. Okay, so d. Okay, so you can see this is the original system. So everything inside here is what? Everything inside here is my observer to get x1, get x1 here. This get out. This one get out for me to do a state feedback. So this one is to provide U and Y to this block. This is called observer, full state observer. Observer, all these coefficients are already decided in this equation. So that's my observer construction. And this can be done in computer very easily. So that's our full state feedback. But you may wonder how we can do the full, how we do the feedback UX minus K X hat. So we haven't done that yet. Okay, we haven't done that yet. Okay. So, but this can be designed similarly using the pole placement idea, and we can design that. But now let's focus on observing this fact that x1 is actually already available through the half y, through this half y. So let's talk about reduced order observer here. So you have the original system, and y can offer part of the states, not all. So how to estimate the rest of the state? So we should talk about reduced order observer, okay? Remember here, we haven't really finished all the design because we haven't even designed here yet. So, but this was covered in the last lecture regarding a full state feedback. So let's ignore that. So let's focus on the reduced order. So let's assume that we'll have n minus m dimensional subsystem. Okay, so A, B, C, and so you have a R input, M output, state dimensions n. Okay, let's assume they are fully observable, A, B, C, fully observable. And let's assume that we have a matrix Q that can be partitioned as D and C, okay, D and C. So the reason we do this one is because we can write a partition, okay, this Q here. We can do this coordinate transformation in such a way that the A matrix can be done via the similarity transform matrix Q in here. So we have a partition like this. So in this partitioner case, B is QB, so you have two parts. But in the C, Q, this one is 0. Okay, this part is 0. Basically, I block the first part. Then I have only I in here. So that's the partition matrix. Okay, partition matrix. So after the partition, my Y becomes only X2 here. X2 here. So we assume that the X2 can be obtained from Y. Okay, so basically Y equals Y can do the partition. Okay, like two parts Y1, Y2, and Y2 itself is X2 bar. Okay, see. So what's left is X1 bar. Okay, so we only need to observe X1 bar here. Sorry. So step 2 is to write the partition form. So Y is X2 only. Okay, X2 only. And remember, Y is M. Okay, Y is M. Y is M. I need to pause for 1 second. So I did some disturbance rejection. Okay. So all this can be written as partitional case. So you can see x1 dot, x2 dot, y is like this. Okay. So I hope we are only focusing on two parts. Okay. The first one is x dot, so a11, and everything here is v. Okay. And we assume that the output is z is a21. Okay, a21x. So this is a21. So this is a full state observer for this LTI system. We are going to construct that one. So V, of course, we have written A12X2 is B1. So this is just V term. And this one can be written as X2 because X2 is known, okay, is Y. So simply write this way. And the Z becomes something different. This is my Z, actually. This is my Z. It will become this one. And this one, X2 bar is Y dot. It's known. It's Y dot. It's known. A22X bar, X2 bar is none. Okay, it's Y. And B2U. So then that means Z is considered as none. Okay. Which is reasonable to say this is Z as output is a none, kind of like output. Okay. This is reasonable, isn't it? Yes. So therefore, for this whole system, how to construct x1 hat becomes a11 minus this one. So this is a standard like what we have seen before. V is a known variable here. V is a known, it's also known variable, okay? Also known variable. Z is also known variable, okay? So then we just put everything in. So V is A1 to Y and B1 to U. So this is V, and this is my Z. This is my V. This is my Z. Okay. So this is none. Okay. This V is none. Okay. V is none. So then we just add this. Consider this is a driving term and add towards that. So x1 hat dynamics. So again, here we have this H in here. This is my H. You can do pole placement as well. So finally, so x1 hat is my, so W is kind of arrow of my measurements, okay, measurements. X hat is arrow plus this. So then after that, you can write W dynamics, okay, W dynamics. And you treat x1 as a W and plus this one, okay. So it's equivalent, okay, equivalent. Just simplify our notation. So n minus m dimensional observer, okay. So the whole thing is like this one and this one. So in other words, this reconstructed x hat is written as this way. Y is HIY. So this is I0, this is W. So that's it. But remember, you need to put X bar back to the original X coordinates, okay? So then you need H inverse here, okay? Okay. And obviously, in the X bar coordinates, the aerodynamics, these are arrows, okay? Estimated is arrow bar, okay? This is arrow bar dot. This one is linked to this H. So H is chosen to make arbitrary pole placement of this guy, and how the rate of decay should be. That's depending on your choice. But X2 bar is directly is Y, so there's no arrow, no transient. So that's good. I know there's some variables as messy. Let me go back and remind you the steps. Okay, they put the steps in here. The step one is you have to extract this n minus m dimensional subsystem. So because you already assume that you have already m. So y is m, okay? Y is Rm. And this one is already said that this is, you can get the x already. Part of the x, okay? Part of x. Okay, it's x2 parts. So let's say x1 and x2, the 2 parts, okay? So I have one part is already known and another part we don't know yet. So the idea is to do a similarity transform, okay, into bar, x bar, okay, x bar coordinates, okay. From x bar coordinates, you'll be able to see the C is C bar is written as the partition apart. So you can see Y is C times X. So that will be the X2 part is already known, okay? Okay, let's do this. Y equals this one. Yeah, X2 bar, okay. X2 bar. So the step 2, we did this partition, then we are going to write the 2 parts, okay, of X bar, okay, X bar. This is transform the system. The A is becoming this partition matrix. And of course, we learned that A bar is QAQ inverse. It's like here. A bar is here. It's here. So the reduced observer design, basically we focus on X1 because X2 is known, is Y, okay? And remember, Y is Rm, so, and this is N by N minus M, the rest, okay? So we'll basically focus on this yellow block. While the V is basically this term, okay? I told you this term. And this term we use known, X2 bar is Y is also known. So this V, okay? And then we assume the Z, this side, okay? This side has a Z, okay? This whole side is Z. So Z becomes A21X1, okay? But on the other hand, Z21X1 is like Z. But on the other hand, Z can be treated as a known output because we can compute it from known Y and known U, okay? So the reduced order observer for focusing on the yellow block here to this block is a full state feedback. No, sorry, it's a full state observer design, similar to what we have learned so far after the similarity transformation. Okay. So after that, we just define some W in here. So in here, we can write W dynamics. So this N-1 dimensional observer with the full state estimation. So you write in the original full format, you know that X2 is Y, X1 is this. So you write some matrix form, it doesn't matter. Okay. After you got X1 hat, X1 bar hat, you need to transfer back to X1 hat. Yeah, you need a Q, you need a Q minus in here. Okay, so exactly this equation. So the third part is H gain. So the H gain is basically focusing on A11, A21, okay? And this is like C, this is like A, so this is the full state feedback design. You can use pole placement depending on how fast you want to decay this aerodynamics. So this is aerodynamics. So the whole thing is called aerodynamics. Okay, aerodynamics. So in a nutshell, basically, this is just a copy of what we had. Okay, so the whole thing is the reduced order system. So basically, you have, oh wait, basically you have the whole thing here. The whole thing here. So this is called reduced order observer. Okay, reduced order observer. But Y is supplied in here, also supplied in here, so that in the end, you get the full state estimation here. But remember, part of that X1, X2, hat, the bar. So basically, we only did X1 hat. Okay, writing in this matrix form is just for notational simplification to be more concise. Now let's return back to our original system. And So here's a system. Here's a system. So this is a system of x1 is x1 plus u1 plus u. x2, x1 dot is x1. x2 dot is also u, okay? So the u will determine the x2, u will determine this one. So the whole system is controllable because you have a Jordan block like this, okay? So this is all controllable, okay? And of course they are observable, okay? So it's both controllable, both observable. But here we focus on the observer design. So we do first order observer, meaning I only construct one. So in this case, let's focus on, this is like y is 2x1 minus x2 is my y, okay? It's my y, okay? So what I'm going to do here is only focusing on the first order, okay? In this case, I'm trying to make my C matrix like this one, I only want to observe. I want to observe x1, okay? Okay. While x2 is none, precisely, real y. So we assume my x2 is fully none, okay? We can do some similarity transform like this Q to make the CQ inverse like 0, 1, okay? I think we should have C bar in here, okay? Q times B, it is still Q times B is 1, 1, is still 1, 1, okay? That's good. But A becomes 0, 0, 1, 1, okay? This is like controllable form, okay? Eigenvalue of, we put observer at minus 10. So here I only have one H. So lambda plus H is my, so this is the eigenvalue of A11. Here A11 is 0, okay? H here A21 is 1, A21 is 1. So by doing that, I know that H should be 10. So in this case, H is 10. So we write the reduced order observer. This first order, we only do one observation, okay? So it's A11, A21 here. That equation you can just make use of it. Don't have to rederive it. But good thing is this is called a systematic way. You will never make a mistake by doing that. So let me see, yeah. So Y is known, U is known, A, B, C, all these matrices are known, H is also known. So with that, any W0, okay, W0, it doesn't matter, you will have W coming out. So this is the W equation, differential equation. So then my overall in the coordinate system, transformed coordinates X bar hat, it will be written as W and Y. It becomes this way. This is not the end, so you have to convert to X hat, okay? So then X hat is a Q inverse, so you got this one too. And W signal, Y signal are assumed none, so what you should do? So U is here, this is my U is a known signal. And you have Y in here, so this is a Y, it's also known signal. based on U and Y, okay, you can construct X and X2. But basically, we didn't do anything on X2. We only did X1. So the reduced order observer W is this one, and this one is shown in here. This one. Okay, this is observer dynamics. This is the same thing here. Same thing here. So original system is this. You construct the W dynamics driven by U and Y. You are going to get a W. And then using W and Y with this one, you are going to recover X hat. So then if we draw a block diagram, so these are the unknown. These are the unknown initial conditions, okay? Initial conditions. But that doesn't matter. No matter what is your initial condition, everything will converge to the equilibrium point, okay? And exponentially, okay? Because this is a LTI system. Anyway, right? Anything stable is exponential stable and asymptotic stable. And all stability notion applies. Equivalent. So what I'm trying to say is this is from U to Y. That is the original dynamics. So X2 hat integration will be X2 and X2 minus. So this is like my original C. This is A matrix from here to here. So go back. Yeah, it's here actually. So you can see x1 dot plus equals x1 plus u. This is my u plus x1. Okay, so this all plus plus. So this is this equation. This is this equation. Okay, this block. The following block is a little bit different. So you have minus 9 times u is here, minus 9 times u, minus 110 in here, minus 110, so this is plus plus, is y, so this is y, so this term. And you need a minus 10w, okay? Minus 10w here, minus 10w, and we'll construct the y dot. Integrate this one, you get w, and plus the initial condition is w. Okay, so here from here, you're going to see the half of w and 11 divided by 2 times y. Okay, times y is your x1 hat. Okay, in original coordinate. And here you have 1w, so this is 1w. Plus 10y, so this is 10y, this is y, 10y, then you will get x2. So this is shown in roughly here. So all these things you can see, unlike what we expected before, we only used an observer of the first order. Unlike what we believed, if the full state feedback, you have second order, right? Dynamics. But because this system is second order, right? Second order system. This is not second order, it's first order. Yet you can still construct this, okay? Construct this. So no matter what, giving ABC, you can do a state feedback, no matter it is a full order or reduced order. Okay, then finally you can design the K, Then there are infinitely many choices of the K. Okay, choices. But in the pole placement, you give the pole position, then you will have a unique K corresponding to that, which is good. But the question is how you can put all those places, positions. That is a topic of research. Okay, so let's do another example. Okay, so this is a second order system. This is a typical position servo. Okay, position servo. So usually it's like you have a voltage applied to a system. You will have a S+6. So you have the wait. You have this one. So usually this is a driving voltage. Then you will have omega. Yes, turning. Motor is turning. And omega goes to an integrator, you got a theta, right? So that's why I keep saying this is a position servo. This is a position. This is a control voltage, okay? Voltage. So we use state feedback, make the closed loop system pull at this position. We implement the state feedback using two types of observers. One is a full state, two-dimensional. One is a reduced order. Okay, reduced order. Reduced order. So solution is, first of all, we need to find out this G of S to ABC, that is minimum realization. And using observable canonic form, okay? Observable canonic form is here, okay? It is fully controllable, okay? So solving the state feedback matrix. So this is a K1, K2. Suppose you have a X, okay? Suppose you have this full state available. So this CP stands for characteristic polynomial. Characteristic polynomial. So this is Si minus A minus BK, and so the determinant of that, okay, is a determinant basically. So you got this polynomial, but here we said that this characteristic polynomial should have a complex conjugate pair like this. Then we just, this is a pair of complex conjugate pole, end up with this polynomial. So by comparing the coefficients to here, it's easy to check. This is a K1 is 2, K2 is 40. So this is a full state feedback if we can do that, okay? So I have K already. So now we cannot assume the X hat is all known, or X is all known. So we don't assume that. Let's assume that we do observer design. Two-dimensional observer design. So, and also I assume that characteristic polynomial all place a minus 10. So there's a rule of thumb here. I can tell you, but this example shows it. So this is like minus 4, right? And this is one pole in here, another pole in here is 4 plus or minus J6. So here is 6, here is minus 6. So this is minus 4, right? So this is S is minus 4. So these are the two poles, and they are, what's the distance between the two poles to the imaginary axis? That's 4. So the rule of thumb, you remember, okay? Is your pole of your observer should be left of this one by at least like 2 times, like minus 8, or so this is minus 8 and minus. So here we put minus 10 here. So So this is minus 10. So in other words, this one transient decays much faster than the closed loop desired behavior here. So this rule of thumb is you need to be left at least 2 times, okay? Faster, so it decays 2 times faster. So that's why it's minus 10, okay? So if you say, oh, I do minus 2, is it good? Very good question. People already checked this. This is a problematic, okay? So you are slower than your pole decay rate, so it's no good. Your overall performance, it will be problematic. So this point about choosing the pole position of observers is something maybe some textbook will mention the designing issue. But here I just tell you rule of thumb is 2 times bigger or further left. So in this case, s plus 4 square will give you a polynomial like this. Then you compare the coefficients. You are going to get h1 is 100, h2 is 14. Okay. So I got a K matrix, I got H matrix. So full state feedback we have learned is very easy. It's a full. So then I don't have to do a coordinate transform. I simply copy the system dynamics. Okay. So then I have a minus HY is minus HY. Sorry, Y hat. So then this is nothing but minus HCX hat. So this one goes to here, you get this term, and B is original one. This is a correction of the real measurements. So after we computed, everything will be like this. So remember, Y is known, U is known, and X, you know, X hat 0. It doesn't matter what's the 0 here. So basically, remember my K is 240, okay? Remember my H is 116. 14, okay, sorry. 14. So you can see 240 is here. So there's K1, K2, X1, X2 hat. So, okay, so these are the outputs. So this is my U, this is my Y, okay. So these are the gain for the Y, so 114, so 114. So then if I draw this diagram, so this is my full order observer, full order observer. So then the whole thing, closed loop transfer function, closed loop dynamics will place my poles at -4 plus or minus J6, remember? So for overall from here to here. Okay? But it's wrong, actually. It's wrong. So from here to here, the whole system, what's the order? It's order of 4, okay? Because original system is order of 2. And here, observer is also order of 4, order 2. So add together is total from V to Y is order of 4, okay? Order of 4. So then your characteristic polynomial of this whole system should be here and where? -10, remember? So the closed loop pole should be 1, 2, 3, 4. Okay, 1, 2, 3, 4. That's a full order observer. So now let's say I only have luxury to use first order observer. What I'm going to do, okay, what I'm going to do. So this case, our desired characteristic polynomial of this is this. So I can choose H is 10. So this is a reduced order observer by using this equation. So we end up with minus 10W U and minus 40Y. Okay. So then we can write X here. So this X2 is Y. Okay. So then this is Y plus 10Y. So W plus 10Y. So here. So again, so this is like K already did 2 and 40. Okay. 40. So then I have U come over here to construct the 1U. 1U is here, minus 10W. So this is minus here, okay? This plus. And U minus 40. So this one is minus 40, okay? So this is minus 40. So you construct the W dot. The W dot is this one. Okay, we'll put a minus here, okay? So minus here. So then this is a plus. So we construct the W, and interesting, W going here, okay, plus 10 Y. So this is the Y, okay. So you can get X1 hat estimation. But X2 hat and Y are the same, okay. Okay. So the whole thing, observer is going from here to here. In is U, in is Y, output is X1, okay, only reduced order, okay. So, but now you have a K in here. So the overall system will be 2 plus 1 order, okay. And the closed loop pose will be minus 4 plus or minus J6 and minus 10. So this is a state feedback. This is my reduced order dynamics. So that's it. One-dimensional observer design. Okay. So because I know Y already can count as my X1 is X1. Very good. Reduced order design. And these equations, if you cannot remember, you don't have to. You just go and check it out. Just do the partition of the matrix. So the summary is we did the full order observer design. We discussed about steps for reduced order observer, which is more practical. Okay, practical. Maybe a little bit tedious, but the procedures is systematic. We did actually 2 examples on this. So next time, so we are going to do linear quadratic regulator. In fact, this topic is a little bit involved about 2 parts. One is called finite time. One is called infinite time. Well, why I say that? Okay, so I'm going to give you a preview of what we are doing here. Please read this part and let me give you a rough idea here. So you have X dot is AX plus BU Y is CX, okay? Suppose you can do all the state feedback and pole placement, but you never know whether your X transpose x, and u transpose u. So these are the quadratic cost. Like if I write a scalar form, you have x squared, right? You have u squared, right? So this is a kind of energy, right? This is a kind of energy, but it's instantaneous energy, a power. So power. So what is the energy then? We should integrate this. Yeah, integrate this one. Okay, from T0 to TF. Okay, yeah. And of course, we can add a weighting filter here and say, for example, usually this is put R matrix. This is put a Q matrix. So the R is a positive definite matrix. Could be symmetric. So Q is positive definite. So then, of course, the special case is I, right? Special case is I. We add them together, and so this is my generalized cost. We can put emphasis about, it's like weighting, okay? Weighting matrices. Weighting matrices, QR, okay? QR. So I'm trying, so giving A, B, C, Q, R, given T, given TF, okay? So what is change? The U is changing, okay? U is changing. So if I choose different U, be careful, I'm a U of T in here. So this is a scalar, okay? This is a scalar. J is a cost, okay? So it's a cost function. Okay, or performance index, okay? Performance index. Uh-oh. What I'm doing. Performance index. Okay. So remember, this is not a parameter. If you say, oh, this is if we have a parameter, and then if say U is a constant, so then what is the U? So you are choosing the best value of U. If you use a constant, you can choose the best value of U. But now you have a U is a U of T is a value or parameter versus a curve or time function. So how many points of the U of T is infinite values. So, it's not possible to, what I'm doing here, why I keep getting this, yeah. So you have infinite parameters to describe the U of T, okay? So if you have learned minimization or optimization or maximization or stuff, so you have a, say you have a function of f(x), so you have a minimum of x, so you simply do partial f partial x is 0, you get the necessary condition. Then min and max is not sufficient, you have to check second derivative and so on and so forth. So you can solve the x, but right now x is constant. It's a value or vector. Okay? There exists a value to make this one x always less f of x for all x. Okay, so that's called parametric minimization or maximization. But remember here, you are not having a constant parameter in x in here, variable in here. You are having a curve. Okay, you have a curve. So in other words, you have a curve U of T that you can change by choice. Okay, you choose U of T, and it's U of T is a function of T. Now I'm have another function of a function So this is called functional. Okay, function. So in a real analysis, you are going to learn, you need a real analysis. There's a course called real analysis. Okay. So the idea is you have a linear LTI system, you know everything. What do you want? Okay. What do you have? You have A, B, C, Q, R. What do you want? I want this to be minimized by choosing a best U. The best U is also called optimal control. But here, I'm talking about optimal control. It's an optimal control signal, meaning it is a function of T, okay? Function of T. So solving this problem is non-trivial. It's non-trivial, okay? Especially when TF is not infinity. It's non-trivial, okay? It's non-trivial. It involves a separate knowledge on calculus of variation, okay? Pontryagin maximum principle. You need Pontryagin maximum principle. You need a co-state. You need a Hamiltonian. Okay, you need a co-state equation. So all these concepts, okay? So to get this problem solved, so it is very involved. It's very involved. So never underestimate LQR. If you don't have a solid foundation on QR, so you have no way you can do a sophisticated research in control, okay? So my job here is to make sure you have a right picture and preparation for the future. And so next lecture is quite important, so don't miss. And we are going to have a help session on next Monday, discuss about homework 8 or 9. 9, yes. And also maybe we'll have some time to discuss about FISP if we have some questions. Email me. And so we are done today. Do you have any questions regarding this? I'm not trying to scare you about LQR. Okay, I just say that LQR is important topic. And a lot of people thought they learn LQR. It's not. There is a wonderful magic that when TF is infinity, the UT actually can be written as a minus KX. There's optimal K there, and K is constant. Full state feedback. This is a beautiful part. Okay. But remember, it's different. I'm writing U of T here. This is called control law. And here I'm talking about, I only need a control time function. There's a fundamental difference in here. And from UT to UT equals KX, there is a giant leap. Okay. That's it. So I'm going to stop sharing. You have any questions? You have 2 more minutes. So, and I'm going to upload the recorded lecture again. So we're not going to miss any recording this semester. So keep a copy for memory, okay? Questions? If you don't, I count 3, we are going to end the meeting, okay? Sorry for my cat giving me some disturbance. It's my mistake, I didn't close the door. All right, so have a good weekend and be safe.
Thank you. You too.
Goodbye.
Thank you.
Good.
Okay, bye-bye.
Bye-bye.
Thank you.
See you Monday.